Hello, everybody, and welcome to this week's lesson. This week, we're going to be talking about evaluating and comparing functions. And specifically, we're going to be focusing on linear functions, which we've talked about before, as well as quadratic functions. So by the end of this week, you will be able to evaluate linear and quadratic functions for values in their domain when represented using function notation. We're going to talk about all those terms in that sentence there. And we're going to compare properties of two linear or quadratic equations, each represented in a different way. So that's algebraically, numerically in tables, graphically, or by verbal description. So those different ways of representing functions that we've already talked about in previous lessons. So specifically what we're building on here are lessons from the week of June 8th to June 12th, where we had an introduction to functions and graphing, and then also our lesson from the week of June 15th to June 19th, where we focus specifically on linear functions and proportional relationships. So I'd highly recommend that you go back and watch or re-watch the lessons from those weeks, get out your notes from those lessons, and get out any assignments that you've completed for those lessons as well. Those will be helpful to refresh your memory. All right, we got a warm-up problem for you here. So for this problem and the rest of the lesson, besides those notes, I'd also recommend that you have pencil and paper, and you might want a calculator as well. A calculator isn't absolutely necessary, but you might find it useful. Okay, so I would recommend pausing the video and giving this problem a try, and then we're gonna come together and do it together, make sure you got the right answer. So this question says, determine which of the four options represent functions. Select all that apply. Okay, so first thing we need to do is we need to remember what a function is. So a function is a relationship between input and output, or between x and y, where there's exactly one output for each input. So that's the basic definition of a function. Is it's the special kind of relationship between input and output, or between two variables, where there's exactly one output for each input. So we're going to go through each of these options and see if they meet that definition of a function. So let's start with option one. We've got our input here in the x column, and we've got our output here in the y column. So we want to see for each of these inputs, is there only one output? So for -2, the input of -2, there is only one output. -2 is only giving us 4. -2 doesn't show up anywhere else in this input column. It's not corresponding with any other output, so that's good so far. I'm also seeing that for -1. -1 is only giving us an output of 1. 0 is only giving us an output of 0. And 1 is only giving us an output of 1. So that looks like option number 1 is a function, because there is exactly one output, one y value for each input, each x value. All right, let's move on to option number 2. So option number 2 is showing us a graph. So we need to recall how we determine if something is a function by looking at the graph. And the way that we do that is called the vertical line test. So we use the vertical line test to determine if a graph shows us a function or not. We either imagine or we draw vertical lines through the graph. And if those vertical lines only cross the graph once, then it is a function. If they cross the graph more than once, then it is not a function. So you could just visualize this in your head, or you could start drawing some vertical lines. So I just draw a vertical line here. That vertical line is only crossing the graph, so only crossing that blue curved line at one point. Same thing here. If I draw another vertical line, it's only going to cross once. Only going to cross once. So it looks like anywhere I would choose to draw a vertical line through this blue curve, it is only going to cross the blue curve at a single point. So that means option 2 is a function. All right, now let's go to option 3. So we talked a little bit in our lesson on linear functions and proportional relationships. We talked about how to recognize linear functions written as equations. So you want to think back to that lesson, maybe take out your notes from that lesson and the practice problems. But the way that we recognize a linear function is that, well, one way we know it's a linear function is that it has the form y equals some number times x plus another number. So if anything, any equation we're looking at has that form where it's y equals some number times x plus another number, then we know that that is a linear function. Another way to say it is that a linear function is going to be one where the x, or the input variable, doesn't have any exponents or roots on it. It's also not in the denominator of any fraction. So we can see that that's true here as well. We just have regular old x. It's not x squared. It's not square root of x. It's not 3 over x, nothing like that, just regular old x. So option 3 is in fact showing us a linear function. And if it's a linear function, that means it's definitely a function. If we were to make a graph of this, it would be a nice straight line going at a bit of a diagonal. So option 3 is a function. And then let's take a look at option 4 here. So we've got another table, another numerical representation. So let's see, -2, the input of -2 is giving us an output of 1. Is -2 going with any other output? No, right? -2 just shows up once in that input column. So -2 is only giving us an output of 1. Same thing for -1 here. -1 is only giving us an output of 1. 0, same thing again. 0 only has an output of 1. It doesn't have an output of any other number. 1 only has an output of 1. And 2 only has an output of 1. So this does in fact meet the definition for a function. Each input has exactly one output. Now I could change this. Let's say I added another row to this table. And let's say I said 2 for input and 3 for output. Well, now this would no longer be a function because we would have this input value of 2 giving us 2 different output values. It would be giving us an output of 1, and it would also be giving us an output of 3. So that would be an issue. That would make it not a function. But since that's not actually the case here, this is a function. And you don't want to be tripped up by the fact that all of these inputs have the same output. That's fine. They can all have an output of 1. What's important is that each input only goes with one output. And if we were to make a graph of this, what we would have, so we'd have our x and y axes. So it's our y-axis and our x-axis. So we would have a horizontal line. This is telling us that no matter the x value, we always have, just to pretend that's a nice straight horizontal line, no matter the x value, we always have a y value of 1. So it's just a flat line. We're always at a y value of 1. So all 4 of these options are functions. Okay, so let's go back over that, talking about what is a function and what is a linear function. We already had to start thinking about that with our warm-up problem. So what is a function? A function is a relation between 2 variables, usually called input and output. Input is often represented by the letter x, and output is often represented by the letter y, where there is exactly one output for each input. And if we're talking about a graph, the graph is something that passes, it passes what test? It passes the vertical line test. So vertical line test. Again, I apologize for my writing on here. Working with limited equipment at the moment. So it passes the vertical line test, which we just saw with option 2 in that warm-up problem. Okay. So then what about linear functions? So linear functions, they're called linear because they show a straight line if we're talking about the graph. How do we identify them? So a linear function is a function with a constant rate of change between input and output. So that means the way you get from one y value to the next y value is always the same. It's kind of like a set of stairs. You're always kind of going up, over. You're going up by the same amount each time. It's a constant rate of change. What's another word we have for rate of change? So another word we have for rate of change is slope. So anytime you see that word slope, you know it means rate of change and vice versa. So slope is another word for rate of change. If we're looking at the graph, again, like I just said, the graph is going to be a straight line. And then if we're looking at the equation, we know it's going to be a linear function if it has no exponents or roots on the input variable, and the input variable is not in the denominator. So it's kind of a nice plain set of variables that you got. You got your y or your f of x, and you've got your x. And let's actually put down that function notation here. So we said a function is a relation between two variables, input and output. Oftentimes the output is called y, but it can also be called f of x, which is short for a function of x. Just two different ways of saying the same thing. And this f of x is known as function notation. And you might actually see other letters used. So you might see something like g of x or k of x or b of x. You can actually use any letter you want. All right, so we said one of our goals during this lesson was we want to be evaluating linear and quadratic functions. We need to talk about what a quadratic function is. So quadratic functions, quadratic equations means basically the same thing, right? An equation is just one way that we can show or represent a function. So what's specific about a quadratic function is that the highest power or exponent of the input variable is 2. So you've got an x squared in your equation. That's what makes something a quadratic function. And if you look at the graph, it's a special type of a curve. The curve is known as a parabola. So I've got an example right here. This red curve that you're seeing is a parabola, this special kind of, it's like a U, but it's a U with like a skinny curve at the bottom. So it sort of comes inward. That's a parabola. And then I've just got a couple more examples here of quadratic functions. So this first one says y equals x squared. This is our most basic quadratic function. Most basic, where the output is just the input to the power of 2, or the input squared. And then I've got another example with a little bit more to it. So y equals -1/2 times x squared plus 3 times x minus 1. Again, the highest power or exponent that we see there is 2, and that's what makes this a quadratic function or a quadratic equation. For both of these equations, if we were to graph them, we would get that same parabola curve. Okay, so now that we've had a little bit of work with linear functions and we've seen what quadratic functions are, now we're going to get some practice with evaluating functions. So if you have done any work with evaluating expressions, this is a very similar idea where you are given a number to work with and you're going to do some calculations based on that number. So to evaluate a function, you're given a number for x or y, and you need to calculate the value for y or x. Typically, in the situation we're going to be focusing on today is where we're given a number for x. So we're given a number for the input value, and we need to calculate the output or the y. And remember, y might also be written in function notation. It might be written as a function of x. So we're going to be evaluating linear and quadratic functions for values in their domain when represented using function notation. So values in their domain just refers to input values. So again, you're going to be given an input value and you're going to calculate what the corresponding output value is. And then function notation, again, that just means that we are talking about f of x instead of y. So let's do an example together. Let's look at this example here. It says evaluate f of x equals 4x for x equals 2. So what that means is I'm going to take my function. This is a linear function, and I'm going to evaluate it for when x is 2. I want to figure out what is the output for this input of 2. So I'm going to take that equation that I was given, that 4x, and I'm going to replace it. I'm going to replace the x with 2. So this function of 2 is equal to 4 times 2. And that is going to give us a result of 8. So that means that for this function, when x is 2, the input is 2, the output is 8. Again, there's no special reason why I chose 2 there. It was just one of the possible input values I could have chosen. It was just a random example. That's really all there is to it. We're given a function. We're given a specific input value. So you replace x with that input value and you do the calculation that's laid out in the equation to determine the output value or the f of x value. Okay, let's do a couple of practice problems here. So again, I would highly recommend that you pause the video here, see if you can give these problems a try, and then we are going to go through them together. All right, so number 1, it says given the following equation, fill in the chart for all values of f of x. Okay, so we've got this equation, f of x equals 2x squared plus 1. And then I've got this table. This table is giving me a list of 5 different input values. So 5 different possible values of x. And I want to calculate the corresponding output value, the corresponding f of x. So this is very similar to these tables we saw in our warm-up problem where we're shown some input values and the corresponding output values. Now it's just going to be our job to calculate the output values. So for this first one, we're saying x is -1. So we need to replace x with -1. So we have 2 times -1 squared plus 1. So you could either punch this all into a calculator, or you should be able to do this in your head, or just with a little bit of scratch paper. So let's follow the order of operations here, right? PEMDAS, parentheses, exponents, multiplication and division, addition and subtraction. So we're going to take care of our exponent first. We're going to do -1 squared. -1 squared means -1 times -1. -1 times -1 is +1. So this means we actually have 2 times +1 plus 1. Okay, so we took care of our exponent. Next on the list is multiplication and division. So we're going to take care of this multiplication. So 2 times 1 is 2. Bring down the rest of the calculation. And now all we have left is addition. So 2 plus 1 is 3. Okay, so for this particular function, for this particular f of x, when x is negative 1, f of x is going to be 3. All right, now let's try the next one. So 0, we've got 2 times 0 squared plus 1, and we're going to work through the same order of operations. So 0 squared, that means 0 times 0, which is 0. So we've got 2 times 0 plus 1. 2 times 0 is 0 plus 1 is 1. So for this particular f of x, when x is 0, f of x is 1. Okay, and the next one here, we have an input value. Just erase some of it there. We have an input value of 1. So first thing we do is that exponent, 1 squared. 1 times 1 is just 1. So then we have 2 times 1, which equals 2. Finally, we get to that addition. So 2 plus 1 is 3. We get the same output that we got for negative 1. Okay, next on our list is 2. So I'm going to replace now that x with 2. 2 squared, or 2 to the power of 2, means 2 times 2, which is 4. So we have 2 times 4, which is 8. 8 plus 1 is 9. So when our input is 2, our output is 9. And finally, we come to our last value here. Our input value of 3. So when x is 3, we have 3 squared, 3 to the power of 2, which means 3 times 3, which is 9. And then 2 times 9 is 18. And 18 plus 1 is 19. So when x is 3, f of x, or y, is 19. All right, so we have filled in our table here. We have evaluated this function for these 5 different inputs that we were given. All right, let's move on to the second problem here. For input k, the function f is defined as f of k equals negative 2k plus 1. What is the value of f of negative 8? Okay. So this one is written a little bit differently, but it's really asking us to do the same thing. We're given a function, and we can see here we've got this input variable of k, which is going to give us an output of f of k, or a function of k. So they say, what is the value of f of negative 8? That means negative 8 is the input value we want to use. So f of negative 8 means I'm going to replace the input variable with negative 8. So negative 2. And instead of k, I'm going to put negative 8 plus 1. Okay, so now it is a matter of doing the calculation, following the order of operations. We don't have an exponent here. All we have is some multiplication, right? We've got negative 2 times negative 8, and also addition. So we're going to do our multiplication first and our addition second. So negative 2 times negative 8 is positive 16. Right, with multiplication and division, two negatives make a positive. So we have 16, and then I'm going to bring down that plus 1. Our final step is to do that addition, and we get a final answer of 17. So for this particular function, f of negative 8 is equal to 17. That means when we put in negative 8, all right, and we just had a little blip in the internet, but we're back online. So as I was saying, when you, for this particular function, f of k, when you put in a value of negative 8, you get out a value of 17. Okay, so we've come to our next skill that we're going to practice today, and that skill is comparing functions. So our learning goal is that we should be able to compare properties of two linear or quadratic equations, each represented in a different way. So that could be algebraically, meaning with an equation. That could be numerically in a table, or it could be graphically, visually with a graph, or just by a verbal description. So what can you compare if you're given two functions? Well, you can compare slope. If you have two linear functions, you can compare their slope or their rate of change. So in previous lessons, so our lesson on linear functions and proportional relationships, we had some examples where we were comparing two linear functions, meaning two lines. And we might have one line that looks like this in red, and we might have another line that looks like this. It's red again. Come on, green. There we go. We might have another line that looks like this in green. And we could compare their slope. So we could look at this red line and this green line, and we see that this red line has a greater slope. It has a higher rate of change. It's increasing, getting bigger at a faster rate. So another thing we can compare between functions is we could compare output values for specific input values. So if we return to this red and green line here, let's say we're talking about an input value of 1. So, right, we're talking about x equals 1. Well, for x equals 1, we've got our green line here is the output is right here on the y-axis. Let's say that that's a 1 on the y-axis. I know I don't have any labels, but let's just say that's about 1. And for our red line, that is about here on the y-axis. Let's say that's something like 4, right? So for this one input value of x equals 1, we could see that the green line is lower, right? The output is lined up with y equals 1, and the red line is lined up with y equals 4. And again, I just made those numbers up, but just to give you a quick example. We can also compare minimums and maximums. So this is something that will be especially relevant when we're talking about quadratic equations, so when we're talking about a curve. But minimums and maximums means lowest values and highest values. So lowest possible values, highest possible values. The minimum means the lowest, the maximum means the highest. And so again, just to give you a quick example, get the blue back here. So let's say we had two quadratic functions graphed on this. I'm just going to put them on the same graph. So we've got one parabola in red here. And we've got another parabola in green. So when comparing these two functions, we could say we're looking at the minimum y value, so the lowest y value for these two functions. So the red parabola, the red quadratic function, is lowest. It has a minimum right about here. The green parabola has a minimum right about here. It has its lowest y value. And so we could say that the minimum value for the green parabola is lower than the minimum value for the red parabola. Or we could say that they have different minimum values, right? We could just look at that. We could compare those minimum values, those lowest values. And then finally, another common comparison that we might be asked to look at is to compare the intercepts. So intercepts come up a lot, especially when we're talking about graphs and functions. Intercepts are where the graph crosses the x-axis or the y-axis. So for example, for this green parabola here, this green parabola is crossing the x-axis over here and over here. So it has these two x-intercepts. And it's crossing the y-axis down here, somewhere in the negative realm. So it has a y-intercept right here. So that's what we mean when we say intercepts. It's important to note that when we're talking about a y-intercept for any graph or any equation, when we're talking about a y-intercept, that's going to be the point where x is 0. So x is 0, and then we've got some y value, some output value. And then for an x-intercept, it's kind of a similar idea. It's where our y values are 0. So x-intercept is we're going to get some x value for y is 0. So for example, if we return to this green parabola here, we can see that, right, the green parabola crosses the x-axis, right? Remember the horizontal axis is the x-axis. The green parabola crosses the x-axis at these 2 points. It has 2 x-intercepts, which is fine. It has 2 x-intercepts, and you can see that those x-intercepts are lined up with where y equals 0 on the coordinate plane. And we're going to see some more examples of this that are a little bit clearer than my quick little sketch here. But just to keep, this is something to keep in mind as we go forward talking about intercepts. Okay, so let's get some practice with comparing functions. So this says a function has a rate of change greater than the graph shown below, and have that covered up on my screen, and less than the table shown below. What could be the equation of the function? Okay, so a function has a rate of change. What's another word for rate of change? Slope. A function has a slope greater than the function that's shown on this graph, so greater than this f of x function over here, and less than this g of x function. What could be the equation of the function? So this is a problem where we get to come up with an equation that meets these requirements. So the function we are creating, it has a slope greater than the slope shown on this line here and less than the slope shown in the table. That means we need to figure out what those slopes are so that we can pick something in the middle. So let's start with the graph. Let's figure out what the slope is for this graph. Now, probably the easiest way to do that, the easiest way to determine the slope of this red line is just we're gonna do a visual inspection of this line. So let's pick a starting point. I'm actually going to pick the y-intercept as my starting point. You don't have to, but I'm just going to pick that point for now. I'm going to pick this y-intercept. And what I want to do is I want to figure out how much do I need to go up and over to get to the next point that I'm going for. And usually what I want to do is I want to pick a point that crosses at nice whole numbers. So I wouldn't want to pick um, a point like this because you can see it's sort of in the middle for the y value. It's in between 0 and 1. We don't want that just because it's going to make our lives harder. We're going to be doing some guessing. We want to pick a point that's sitting on the grid line. So that has nice clear numbers. So I'm going to pick this point here. This is actually the x-intercept. Again, you don't have to pick the intercepts. I'm just doing that for this example here. So now to figure out the slope, I need to determine how much do I need to go up and how much do I need to go over to get from my first point to my second point. Well, I will need to go up 1 space, 2 spaces. So I've gone up 2. Remember, slope is change in y compared to change in x. So vertical change compared to horizontal change. So I've gone up 2, and then I'm going over 1, 2, 3, going over 3. So I've got this rate of change of 2 over 3. Can I simplify this rate at all, 2 over 3? No, I can't. This is already simplified as much as possible. So this is the slope. This is the slope for this graphed linear function here. So my slope is 2 over 3 or 2/3. Right, so 2/3, we've got this fractional slope here. So it's a little bit less than 1, right? 2/3 is a fraction, a little less than 1. Okay, so now let's take a look over here at the table. So again, we are trying to determine change in y. So up top here, change in y compared to change in x. It's going to be our slope. So let's start examining the changes in x and the changes in y or the changes in g of x, sorry, that we see for this second function in the table here. So I'm going to start with my x values. So going from -2 to -1 is an increase of 1, right? You're going up by 1. Going from -1 to 0 is again an increase of 1. Going from 0 to 1 is an increase of 1. Going from 1 to 2 is an increase of 1. Now let's take a look at the outputs here. So going from -3 to -1 is an increase of 2. Going from -1 to +1 is again an increase of 2. 1 to 3 is an increase of 2. And 3 to 5 is an increase of 2. So here again, we can see that constant rate of change. What we're seeing is that each time our input goes up by 1, our output goes up by 2. And so we could say that our change in y, or our change in output, is 2 compared to our change in x of 1. So we've got 2 over 1, and we can simplify that. 2 over 1, we can just write that as 2. Okay, so this means that we want to create an equation, a linear equation that has a slope that is between 2/3 and 2. Let's see, our first function was called f of x. Our second function was called g of x. Let's call our function m of x. So let's remember that linear functions, one way we can write them is actually, I changed my mind. I'm not going to use the letter m. Let's use the letter j. So we've got this function that we're going to create, j of x. So yeah, we want to remember that linear functions take the form mx plus b. So the slope times x plus the y-intercept. So mx plus b. And since this problem is asking us to basically create an equation, right? It says what could be the equation. We just need to come up with something that works. It's going to be our job to pick the values for the slope for m and for the y-intercept for b. So let's think about b first. B is the y-intercept. That actually doesn't matter here. We can pick absolutely any number we want because this question is just asking us to pick a function that's in between these two slopes. So we really just care about the slopes. The y-intercept is totally up to us. So again, you could pick absolutely any number you wanted. I'm just going to keep it simple. I'm going to say +4. Why not? And then we know our x is going to be here. So the really important part here is we want to pick a slope that is between 2/3 and 2. So we need a number between 2/3 and 2. Well, we know 2/3, it's a proper fraction, which means it's less than 1. So we could actually pick 1 if we wanted to, right? 1 is a number that is greater than 2/3 and it's less than 2. We could pick 3/4. 3/4 is a fraction that's greater than 2/3 but less than 2. We could pick 1.5. We could pick 1.9. There's infinitely many numbers in between 2/3 and 2. But again, let's keep it simple. So I'm going to go with 1 here. So let's just say that our function that we're creating has a slope of 1. So we have j of x equals 1x plus 4. And I'm actually going to rewrite this one more time here. Oftentimes when you have a slope of 1, so you're just saying 1 times x, what you do is you don't bother writing the 1. The reason for that is 1 times any number is just that number, right? So 1 times x. Another way you could say that is it's just x. So the final way I'm going to write our function here is just x plus 4. Remember, if you were doing this yourself, your equation could look different from mine. You could have j of x equals 1.9 x 1.9x minus 7. You could have j of x equals 3/4 x plus 0. You could actually just have a y-intercept of 0. So you could do plus 0 there, which means you actually don't really need to write anything. So there's literally infinitely many things you could write for this specific problem, but there's a few examples to get you started. Okay, so we're going to wrap up our lesson today with a few practice problems. These are more similar to the types of problems you might see on the actual GED test. All right, so number 1 here says, which statement is true about the 2 functions shown below? So we've got 2 functions here. We've got f of x, which is shown on the blue curve, and g of x, which is shown with the green curve here. So before I even look at my answer choices, I'm just going to compare these 2 things myself. I'm going to ask myself what's similar about these and what's different. So what's similar about them? Well, they're both quadratic functions. They both have this parabola curve, this special U-shaped curve here. So they're both quadratic functions. I noticed that f of x seems to go down lower than g of x. So f of x is crossing the y-axis. It has this minimum value of -1. So its minimum value also happens to be its y-intercept here. G of x has a minimum value of 1. It has a y-intercept. It crosses the y-axis at 1. So they have, even though they are a similar shape, a similar type of function, they have different y-intercepts / minimum values here. I'm also noticing that because f of x goes down a little bit lower, that means it's crossing the x-axis. It has these two x-intercepts. It's a little hard to tell exactly what they are because they're in between the two numbers, but it looks like it might be -1.5 and +1.5, something like that. G of x actually doesn't have x-intercepts. It doesn't cross the x-axis at all. So that's another difference. So now I'm going to take a look at my answer choices. Choice A, it says f of x and g of x have the same minimum value. Well, we just talked about how it's not true, right? They actually have different minimum values. F of x and g of x have the same x-intercepts. Again, we know that's not true. F of x has two x-intercepts. G of x does not have any x-intercepts, so they're definitely not the same. Choice C, it says g of x has a higher minimum value. So g of x has this minimum value of 1. F of x has a minimum value of -1. So choice C actually looks true, looks pretty good so far, but let's just take a look at choice D here. Choice D says f of x has a higher minimum value. And that's not true, that's the opposite statement. So we would go with choice C here. G of x has a higher minimum value. It's sitting up a little higher on its graph. All right, number 2, the equations below show the total earnings for 2 employees based on commission. So commission is where you earn a percentage of the sales that you make. I think that's the case a lot of the time if you're working in something like car sales. You earn a percentage of the value of the cars that you sell. So the variable X represents the amount of money the employee has made in sales. So it's like how many dollars worth they have sold for the company they're working for. The variable Y shows the employee's earnings. So basically the cut that the employee gets from the sales that they've made. If each employee makes $500 worth of sales, who will earn more money? So let's take a look at the equations here. It says employee A, their earnings equal 0.2 times their sales. And for employee B, their earnings equal 0.3 times their sales. So there's a couple different ways to think about this question. The quickest way, if you have a good understanding of your functions and slope here, you might be able to see right off the bat that employee B is always going to be earning more than employee A for the same amount of sales, right? Because employee B is earning 0.3 times whatever sales they make. So that's 30% of the sales that they make. Whereas employee A is only earning 20%, 0.2 of the sales that they make. So you actually don't need the $500 piece of information here in order to determine who's going to earn more money for this situation. However, the second way to approach this problem, let's say you looked at your equations and you weren't quite sure, you felt a little unsure because of those decimal numbers in there. The second way to do that would be to actually plug in that $500 and determine the earnings, right? So X is the amount of money we made in sales, so that's that $500. We're going to plug that in for both of these equations. And we're going to do the calculation. So let's start with employee A. We're doing 0.2 times 500, and that is 100. So that means that if employee A makes $500 in sales, their commission, the amount of money they actually earn, is going to be $100. So 20% of 500 is 100. And then let's see for employee B, we've got 0.3 times 500. We get 150. So just like we had predicted with our first strategy, right, just comparing their percent commission, we were able to predict that employee B would be making more off of their $500 worth of sales. We see that that does in fact work out. If you take 30% of 500, right, employee B is going to be making $150 from those sales versus employee A only making $100. So who will earn more money? Employee B is going to earn more money. So in this problem, we were comparing two linear functions that were both represented in the same way. So two linear functions that were both represented with equations, or another way to say that is we had an algebraic representation for these two functions. All right, and then our last practice problem here. Number 3, which statement is true about the two functions shown below? So we've got f of x, which is a graph of a linear function here, right? It's a straight line. This is actually a linear function we've already seen in this slideshow. I just reused the picture. And then we've got g of x over here shown numerically or with a table. So let's take a look and see what we can notice. Let's see what we can notice about these two functions. So we already noticed that f of x is a linear function. F of x is a linear function. It has a y-intercept of -2. And because I remember from the previous slide, I also remembered the slope here is 2/3, 2/3 for f of x. And it has an x-intercept of 3. That might be another useful piece of information. Okay, now let's take a look at g of x over here. So thinking back to what we talked about with x and y intercepts, I can see here I've got an x value of 0 and an output value of -2. That means that this row here is showing me the y-intercept, or the intercept along the vertical axis. We're not calling it y for this specific example, but it means the same thing. So where x is 0 in this function, y or g of x is going to be -2. That means this function, whatever it looks like, it's going to be crossing the y-axis at -2. So f of x had a y-intercept of -2. Looks like g of x also has a y-intercept of -2. And then let's also think about the slope here. So remember, change in y compared to change in x. So x is going from 0 to 1. That's a change of 1. From 1 to 2 is a change of 1. 2 to 3. I think I'm noticing a pattern here. 3 to 4 is a change of 1. Okay. -2 to 2 is an increase of 4. 2 to 6 is also an increase of 4. Again, it looks like we got a pattern going here. 6 to 10, that's an increase of 4. And 10 to 14 is an increase of 4. So for this function g of x, the slope is, well, we're seeing an increase of 4 in the y direction, or for g of x, each time we have an increase of 1 in the x direction. So the slope is 4/1, or we could simplify that to 4. This also means that g of x is a linear function. It has this constant rate of change. So it has a y-intercept and it has a constant slope. So that means these are both linear functions. So let's take a look at our answer choices now that we've done some comparing and contrasting of these two functions. Choice A, f of x and g of x have the same y-intercept. That sounds like a good candidate to me, right? Because we said f of x has a y-intercept of -2 and g of x also has a y-intercept of -2. But let's look at the other choices here. So choice B, f of x and g of x have different y-intercepts. Well, that's not true. Choice C, f of x has a higher rate of change or a higher slope. Well, f of x has a slope of 2/3 and g of x has a slope of 4. So that's not true, right? 2/3 is not bigger than 4. And then choice D, g of x is a quadratic function and f of x is linear. That's not true either. G of x has a constant rate of change, which means it is linear. So the only choice that fits here is choice A. Both of these functions have the same y-intercept. If we were to graph g of x, we would see that we would have a line that was crossing the y-axis at the same point. And let me actually just put this on the graph here. So it's crossing at I've got this point 0, -2. I've got the point 1, 2. I've got the point 2, 6. So if I were to connect these into a roughly straight line, not going to be perfect. That's what g of x would look like, something like that. So you can see it's a much steeper line, it has a much greater slope. But even though it has a greater slope, it has the same y-intercept. It's crossing the y-axis at the same point. All right, so what is on your to-do list for this week? So today, because I was out of the office yesterday, today I'm going to be posting the problem of the day to get us started for our week. I'm going to be posting the vocabulary list and the online learning links. I'm going to post our vocabulary quiz, so that'll all happen today, playing a little catch up from yesterday. And then tomorrow, your Worksheet Wednesday assignment will be posted on the Google Classroom. On Thursday, I'll be posting our Study Skills Part 3 material. And then on Friday, you'll see our second problem of the day for the week. So all of these materials are going to draw from this lesson that we just worked on together. So make sure you go back and rewatch this lesson. Make sure you are taking notes, referring back to the examples we just did together. Thank you all for joining me today, and I hope you have a great rest of your week. Take care.